Today we're going to discuss and go a little bit further into acid-base theory. We started this discussion back in the beginning of the year, but we want to go into more of not only reviewing what that theory is, but to take that a step further and talk about how to calculate and determine how strong these acids and bases are. We talked about different kinds of definitions for acids and bases. The simplest one is the Arrhenius concept. The Arrhenius concept says that an acid is simply a substance that ionizes. We'll take hydrogen chloride gas, put it and bubble it through water, create an aqueous solution, which it means it's going to ionize and form hydrogen ions and chloride ions. Those hydrogen ions are what makes this an acid. The more there are, the stronger the acid is. A base then is a substance that produces hydroxide ions, so we take sodium hydroxide, which is a white solid. We dissolve that in water and it ionizes to form sodium ions and hydroxide ions. And those hydroxide ions are what makes this a base. The more there are, the more basic it is. Now, there are some substances that can't be explained using the Arrhenius definition. So Bronsted-Lowry concept, the Bronsted-Lowry definition, carries it a little step further. It describes acids and bases as being either proton donors, and normally we talk about them in terms of being a hydrogen ion donor or a hydrogen ion acceptor. Remember, you take a hydrogen, which has 99.9% of them only has one proton. They only have one proton in the nucleus. You take that electron away, and what have you got left? Just a proton. So we often use those terms interchangeably, both proton and hydrogen ion. So with the Bronsted-Lowry concept, we have to talk about not only an acid, but also a base. There's always an acid and a base reacting. So in the case of acetic acid, we will treat water as the base. Since acetic acid is a weak acid, it does not react completely. It actually enters an equilibrium state, and therefore we use the equilibrium arrows. So that acetic acid is going to donate a proton, and the acidic hydrogen in any acid that is an organic acid and it ends with that COOH is going to be that end hydrogen. That's one that's going to pop off, if you will. So we get CH3COO minus, and we get H3O plus. We donate that hydrogen to the water. Now, this is actually what exists in water rather than the hydrogen ion. We use the terms often interchangeably. When we ask about hydrogen ion concentration or we ask about hydronium ion concentration, we're talking about the same thing. You've got to learn to think about those two as the same substance. Yes, technically they're not, but anytime you have a problem dealing with acids and bases, they're going to use that term interchangeably. Hydronium ion concentration, hydrogen ion concentration, the same thing. A base then, NH3. NH3 is a prime example of why we need the Bronsted-Lowry definition, because looking at ammonia, there's no way to explain why it's a base because there's no hydroxide in it, there's no oxygen in it. But when you put it in water, ammonia acts like, we often call it a dirty, nasty hydrogen stealer. We call it the pirate. Base is the pirate of the acid-base world because they're stealing hydrogens all the time. So when it steals a hydrogen, it forms the NH4 plus and leaves behind the hydroxide ion. And it doesn't matter how you get the hydroxide ions, whether they were in the compound to begin with or whether it's produced when a hydrogen is stolen from a water molecule. Doesn't make any difference. It still produces that basic solution. So that's the Bronsted-Lowry concept. Now, we didn't say much about the Lewis concept. We did talk about it a little bit when we were talking about ligands and complex reactions. But Lewis acids and bases are defined based on whether they are an electron pair acceptor or an electron pair donor. Two of our prime examples are BF3, and BF3 looks like this. It is trigonal planar. Since it only has 3 pairs of electrons around that central atom, we think of it as having a hole because remember 4 pairs of electrons, 8 valence electrons, that's our like magic number. So it could have 8 pairs of electrons around it, but it doesn't, it only has 3. So we think of it as having a hole around it. Pair that with ammonia. Let me draw that a little bit differently. And ammonia has, it's a pyramidal structure, and it has a pair of electrons, a lone pair of electrons. That makes ammonia an electron pair donor. It makes BF3 an electron pair acceptor. So this is our Lewis acid, this is our Lewis base, and when they react, they simply hook up that way. That pair of electrons simply hooks on to boron, and we end up with this situation. We have boron and nitrogen attached together, that dash referring to a pair of electrons. I'm not going to put in the extra lone pairs on the fluorine, but this is the structure that we get. And this is a Lewis acid-base reaction. And any complex reaction, you can think of it that way. Now, most of the time, we are going to be using the Bronsted-Lowry type of definition, where we have an acid and a base to start with. We're going to have that acid and base. We're going to have a conjugate acid and a conjugate base. The conjugate acid is produced when an acid donates its hydrogen to a base. That base, with its extra hydrogen, becomes a conjugate acid. The acid, now that it's lost a hydrogen, becomes a conjugate base, and that is actually the definition. We always end up with a conjugate acid-base pair, and the only difference between the two that are in that pair are the presence of a hydrogen. So the two conjugate acid-base pairs in this case are HA and A minus, and H2O and H3O plus. The only difference between either of those pairs is the presence or absence of a single hydrogen. So look at this example. It says for the following reaction, determine the acid, the base, the conjugate acid, base, and the conjugate acid base pairs. So often in a multiple choice question, you might be faced with what's one of the conjugate acid, or which of the following is a conjugate acid base pair in this reaction. So let's determine this. First of all, we've got NH3, and if you don't know by looking at it whether it's an acid or a base, then you can see by what's produced. Notice the NH4 plus was made when NH3 gained or stole a hydrogen. So it's a dirty, nasty hydrogen stealer, so NH3 is the base. So if that's the base, it means that NH4 plus is the conjugate acid. And I'm going to label it just Ca. If NH3 is the base, that means that H2S has to be the acid, because if you look at what's formed on the other side, the S2 minus, it has lost some hydrogens. Now, this isn't a balanced chemical equation, but since it has lost this, it's now going to be the conjugate base, since it has lost hydrogens. And honest to goodness, I'm going to change this. I really feel like this should be written as HS minus. So regardless, this is the conjugate base. And so when we react these, or when we start labeling these, then we're going to label the acid as H2S, the base as NH3, the conjugate acid is NH4 plus, the conjugate base is HS minus, and now we're going to label conjugate acid base pairs. So H2S and HS minus are a conjugate acid base pair. In addition, NH3 and NH4 plus are conjugate acid base pairs. So those are some that's just an example of how to label those. I guarantee you on the test I'm going to have you do something just like that for a chemical reaction. Now, in this next example, it's talking about amphoteric substances, sometimes called amphiprotic substances, but these are substances that can act as either an acid or a base. And we've seen all the way through our definitions that we've used water over and over as an acid or a base. In this case, since it's reacting with an acid, water is acting like a base. In this case, in the second reaction, NH3 is a base, so water is acting like an acid. So it is a dirty, nasty hydrogen stealer in the base case, and it donates a proton or a hydrogen in the acidic situation. So it's acting, it can act either way. There are other amphoteric substances. These are substances, again, that can act as both an acid and base. And an example show how HCO3- could act as both an acid and a base. I'm going to react it first with an acid, acetic acid. I use that a lot as an example because AP loves their acetic acid. And I'm going to also show it reacting with ammonia. So it's going to be reacting in the first case as a base, in the second case as an acid. So when it reacts as a base, it's going to be a dirty, nasty hydrogen stealer. So it's going to leave behind acetate because it stole a hydrogen and form H2CO3. Now, when it reacts this way, obviously H2CO3 is one of our bell ringers, and it would continue to react and form H2O and CO2. But I'm going to leave it like this for right now just to make a point. But I will show you, just as a quick reminder, that it would continue to react, because that reaction, if you mix baking soda and vinegar, you're going to get that nice bubbling and fizzing, which is exactly what that first reaction is. So in this next case, we've got it acting as an acid, which means it's going to donate its hydrogen, be very sweet and give it away, which means we're going to get NH4 plus, and we're going to get the CO3 2 minus. So there's two situations, two different reactions where the bicarbonate ion is acting as both an acid, or either as an acid or a base. Now, when we talk about the strengths of acids and bases, we've already studied this at the beginning of the year. Here's the list of strong acids again. I'm not going to go over that. There's no other way to get it but to memorize it. Those are the ones that completely ionize. They have strong arrows. They're not in equilibrium. They're completion reactions. They react completely. Strong bases do the same thing. They're completion reactions. They react completely. Strong bases are hydroxides of groups 1A and 2A, remember, except for magnesium. And also remember the hydroxides of group 2A, like calcium, barium, strontium, they're not very soluble, but they are strong bases. So now when we calculate the strength of strong acids and bases, a couple of things we need to realize. There's something called the autoionization of water. Even when you've got pure water, you have a situation where some of those water molecules are colliding with each other, and when they do, they produce hydrogen and hydroxide ions. Now, we can write it either way. We can write it as the production of the production of a hydronium ion and a hydroxide ion, or we can write it as just splitting it up into hydrogen and hydroxide ions. I will say that I usually write it like this. The equilibrium constant, we sometimes call it the ion product constant. Think about it, since water is a liquid, and I don't know why I've got it as a gas in the second reaction because it's a liquid. But when water is a liquid, it doesn't appear in the equilibrium expression. So all we get for Kw, it's just a special way of writing another way of writing the equilibrium constant. We've already looked at Kc, Kp, Keq. Well, this is Kw, and it's just specifically the one for water because it's so important in acid-base theory. So it's simply going to be the concentration of hydrogen ions times the concentration of hydroxide ions, because we're not going to include, remember, a pure liquid or a pure solid in the equilibrium expression. So very important for us to remember this. Another thing that's very important to remember is that Kw does change with temperature, but at 25 degrees Celsius, which is pretty much how we always deal with calculations of the acidic and basic strength. Both hydrogen and hydroxide are equal to 1 times 10 to the minus 7th molar. So since both of those are 1 times 10 to the minus 7th molar, then Kw, since it's the hydrogen ion concentration times the hydroxide ion concentration, is just simply going to be taking this number and squaring it, which is what we get here. Now, this is probably the only time you're ever going to see moles squared per liter squared, because we just don't put units on equilibrium stuff. But just keep in mind that no matter what the solution contains at 25 degrees Celsius, Kw is going to equal 1 times 10 to the minus 14th for pure water, or for water. No matter what the solution contains. If it's aqueous, Kw is going to be 1 times 10 to the minus 14th. So example, if the hydrogen ion concentration is 3.4 times 10 to the minus 5th at 25 degrees Celsius, what is OH minus? Well, since we know this, Kw is the concentration of the hydrogen ion times the concentration of the hydroxide ion. And we know that if it's at 25 degrees Celsius, at 25 degrees Celsius, if it's pure water, it's 1 times 10 to the minus, I'm sorry, I said that backwards. We know that H plus times OH minus has got to equal 1 times 10 to the minus 14th at 25 degrees Celsius, always. Sorry for the stutter. Then in this case, since the hydrogen ion concentration is 3.4 times 10 to the minus 5th, we're looking for the hydroxide ion concentration. We've just got a nice little equation if we remember that number. Now, you've got to memorize that number. We're going to use it all the time, 1.0 times 10 to the minus 14th. Need to memorize it. So the hydroxide ion concentration then is going to simply be that 1 times 10 to the minus 14th divided by 3.4 times 10 to the minus 5th. We're going to divide both sides by that. And we end up with 2.94 times 10 to the minus 10th molar for our hydroxide ion concentration. Okay, now what if we change temperature though? At 60 degrees Celsius, Kw is this. So using Le Chatelier's principle, predict whether this reaction, the water reaction, is endothermic or exothermic. Okay, well let's think for a minute. The temperature went up, and when the temperature went up, Kw increased. Okay, it went up to 1 times 10 to the minus 13th. So that means if Kw went up, that means it shifted to the right because we produced more products, correct? If it shifts to the right when temperature goes up, then the heat term must have been over here. Remember Le Chatelier's principle. If we increase heat, it shifted to the right and made Kw get larger. What does that mean? Well, if the heat term's on the left, this must be an endothermic reaction. Well, now it wants us to calculate the hydrogen and the hydroxide ion concentration of a neutral solution at this temperature. So remember, it's a different temperature. 25 degrees Celsius is 1 times 10 to the minus 14th, but this is 60 degrees, and this is Kw now. So in order to get the concentration of each of these, we know this. We know Kw at any temperature is going to be hydrogen ion concentration times hydroxide ion concentration. We know this time, though, that Kw is 1.0 times 10 to the minus 13th. And since this is pure water, we know that both hydrogen ion concentration and hydroxide ion concentration are the same. So we can just say this is x squared. So taking the square root of that value, we get that x is equal to 3.16 times 10 to the minus 7th molar, which means that the hydrogen ion concentration, which is equal to the hydroxide ion concentration, is 3.16 times 10 to the minus 7th molar.